Hello and welcome to Math 135. This is Tracy and today we are going to talk about data. We are going to talk about the two sections in our textbook, 2.1 and 2.2. In these two sections we are going to provide information about observational and experimental studies, identify our different types of variables, explanatory, response, confounding, and lurking, classify data as either quantitative, which is also called numerical, or as qualitative, which is also called categorical, and then categorize quantitative data as either discrete or continuous. You have two online homework sets for this. You have 2.1 and 2.2. In addition, you have the text problems listed from section 2.1. There are no additional text problems in 2.2 to look at. So we have two ways to collect the data that we are going to describe, analyze, use to draw conclusions. So our two methods of collecting data are from observational studies. In observational studies, all we do is measure or count something. That's it. Just measure or count what's already out there somewhere. In experimental studies, we are also going to measure and count, but first we're going to apply a treatment. We're going to do something, and then we are going to observe the results. So in an observational study, we don't do anything except observe. In experimental studies, we observe, but after we have applied some sort of a treatment to see what it does. So here we want to determine whether the following study is an observational study or an experiment. If the study is an experiment, what is our treatment? And do you think it's a good experiment? Why or why not? And we will talk a lot more about this in later sections, but now just a brief introduction. So the study we're talking about here, we have a clinical trial of a drug, and 200 subjects are given a 10 milligram dose of the drug. 4% experience headaches. So in an observational study, all we would do is observe. We wouldn't do anything first. But in this study, yeah, we do something first. We give all of our subjects a 10 milligram dose of some sort of medication, some drug. So this is an experiment. This is an experiment because we are providing a treatment, and the treatment is the drug that we are providing. So is this a good experiment? Well, here we have a clinical trial where we just give our subjects a drug. That is never a good experiment because we don't have a group to compare it to. How can we tell what our drug is doing if we don't have a group that's not getting the drug? For all we know, 4% of people would have experienced headaches anyway. So this is not a good experiment. It's an experiment, it's just not a good one. And here I just summarized what we talked about. Our next study, we want to determine whether it's an observational study or an experiment. And again, if it's an experiment, what's the treatment? Is it a good experiment? According to a story in Consumer Reports, 3 major producers of canned tuna agreed to pay over $3 million to settle claims in California that the amount of tuna in their cans was less than the amount printed on the label. Can you believe that? They were trying to sell us cans of tuna that did not contain as much as they said it did. So is this an observational study or is this an experiment? Now remember, in an observational study, all we do is look at what's out there and we observe it. We count something or we take some measurements. In an experiment, we do something. We apply a treatment, and then we look at the results. So with these cans of tuna, are we applying a treatment? No. All we're doing is we're taking the tuna out of the can. We are weighing it and figuring out how much we have. This is an observational study. So we have different types of variables that we can talk about. Explanatory variables are the causes in a study. They explain the results. They explain the response we get. They tell us why things happen. Response variables are the effects. They are the results. They are the responses to the cause. Explanatory variables cause the response variable. Now, it's not always that simple. In fact, it's almost never that simple. Often we have to deal with confounding or lurking variables. And a lot of times these are used interchangeably. Our confounding or lurking variables are just variables that confuse us. They make it unclear what's going on. They may be causing the responses rather than the explanatory variable. And we need to take that into account before we can say smoking causes cancer. We need to figure out all the other things that could be at play. And those are our confounding or our lurking variables. So here we want to look at this description, state the explanatory variable, the response variable, and discuss possible confounding. So we have a weight loss diet meal plan company, and it claims that people who use their diet meals in conjunction with exercise and a healthy lifestyle lost an average of 20 pounds over 3 months. So what is the weight loss company claiming is their explanatory variable? What is this company claiming is the response variable? And what else could be going on? So what this company claims is their explanatory variable is the use of the diet meal plan. The variable, the thing we are measuring, well, not really measuring, we're categorizing. This is a qualitative variable. What category do people fall into? Are they using the diet meal plan or not? So our explanatory variable is the use of the diet meal plan. The response variable, the result of using the diet meal plan, is amount of weight loss. So our response variable is going to be a quantitative variable. We're going to measure how much people lost. Now, our possible confounding, what do they say that their participants are doing in conjunction with the meal plan? Exercise and a healthy lifestyle. We don't know if the people who used the meal plan at the same time said, hey, I'm going to start exercising. I'm going to start a new healthy lifestyle, getting enough sleep and reducing stress and yada yada blah blah blah. So we have possible confounding of these other things that are going on, exercise and a healthy lifestyle. We can't say for sure that the diet meal plan is the only thing causing the response of weight loss. Bias. This is an important word, and we will be talking about it several times throughout the semester. Here we're going to talk about some very basic stuff about bias. Bias is the tendency to systematically over or underestimate the value of a population parameter. Here we have an example. This is a true example. This is my house. We have 2 thermometers outside my house. On a sunny day, the thermometer out front, it could read 80 degrees Fahrenheit. Look out front. Hey, look, it's 80 degrees Fahrenheit outside. But then we look at the thermometer out back, and it reads 20 degrees Fahrenheit. Ooh, what's going on? That's a 60 degree Fahrenheit difference. That's kind of a big deal. One of these thermometers might be systematically over or underestimating the temperature. And why might that be on a sunny day? Well, my thermometer out front is in the sun. As soon as the sun comes up, that thermometer gets hit by it. The thermometer out back is in perpetual shade. So the thermometer out front consistently reads higher than the thermometer out back. Because I can really only read the thermometers when the sun's out anyway, so I can't tell what they say in the dark. There is bias because the thermometer out front on a regular, consistent, systematic basis overestimates the actual temperature outside. So we need to do something to help prevent confounding, lurking variables bias. And the gold standard is to conduct randomized, controlled, also called comparative experiments. These types of experiments help control for confounding. And they do this by putting subjects into two or more groups. And we try to make the two groups the same. We try to divide up our subjects for the study into two groups that are as alike as possible before we start. And then the only thing we change is who gets the treatment. That way we can tell, is the treatment what's causing our results? We randomly assign the subjects to two groups. Randomly. That way everything can sort of average out. We want to help make sure the groups are not different to begin with. And to do that, we don't want to, well, randomly assign and accidentally get all the women in one group and all the men in the other group. So we need to have groups that are big enough, lots and lots of subjects to begin with, so we don't accidentally randomly assign two groups that are very different, because not everything's as obvious as gender. All the little things we want to average out. So we get really big groups, or we do the experiment multiple times with lots of different groups, and then we look at the results of all the studies. That way, if one group is just randomly wrong, came out fundamentally different by mistake, just sort of happens sometimes, we have a lot of other groups to help us see the overall results. Controlled or comparative experiments means that in our two or more groups, all groups are treated exactly the same except for one respect, the treatment. The treatment or experimental group receives whatever treatment we are trying to study. The control group or groups, they get something different. They don't get the treatment. They may get a conventional treatment, so we can compare a new exciting drug to the old tried and true standard to see if the new drug is better. The control group might not receive any treatment at all. They get nothing. Or the control group, the comparative group, the group we're comparing to, might get a placebo. And a placebo is a dummy treatment, a sugar pill, colored water. So people think they're getting something, but they're really not. Then we compare the two groups. Since these two groups supposedly started out the same, the only thing different is the treatment, then it's very likely that any difference between the two groups is due to the, oh, wait for it, it's due to the treatment. This is how we can determine whether our explanatory variable truly explains the response. The treatment is our explanatory variable. Only thing different, it must be what causes our response. So, if subjects know they are getting something, it can affect their responses. This is known as the placebo effect. A placebo is a dummy treatment, and the placebo effect is a positive response. Because subjects believe in something, they actually get better, even if all they're getting is a sugar pill or colored water. It's the power of positive thinking. Hand in hand with that is the nocebo effect. And that's a negative effect. Because subjects believe something is harmful, they get worse. So they think that that sugar pill contains, I don't know, gluten. And so they react, even though there's nothing there. To help avoid the placebo effect, studies are often blinded. In a blind study, also called masked, I think in our textbook and our online homework, not as common, blinded or masked studies means the same thing. Subjects don't know what they're giving. Are they getting the real treatment? Are they getting the conventional treatment? Or are they getting a dummy treatment? Are they getting a sugar pill? In a double-blind study, you have double the blinding. The subjects don't know what they're getting, and neither do the people passing out the pills. Because sometimes if the experimenter knows that he is giving a sugar pill, he could treat the subjects differently. To avoid all that stuff in double-blind studies, nobody knows who's getting what. It's all coded somehow, so, ooh, these numbered treatments are the real thing and these numbered ones are the placebo. So here, we want to answer some questions about a study. A research team wants to study the effects of a new medication to help smokers quit smoking. They randomly divide the subjects into two groups. Group A receives the new medication and Group B receives a placebo. Neither the subjects nor the researchers interacting with the subjects know who is receiving the new medication. So, is this an experiment or an observational study? Well, the key question to ask, is there a treatment? Well, yeah, we're given a new medication. So the treatment for this experiment is the new medication. Is this a good study with a control group? Yeah, we've got a group that doesn't receive the treatment. Group B receives a placebo. This is not the treatment under study, so Group B is the control group. Is this study blind, double-blind, or neither? Well, if neither the subjects nor the researchers know who is receiving the medication, we have two blindings, the subjects and the researchers, double-blind. So in this case, what would be the explanatory variable? What explains our results? In this case, it would be the group, the medication or the placebo. The variable is qualitative because the explanatory variable puts your subjects into categories. The category is either taking the new medication or not taking the new medication. So the explanatory variable is medication or placebo. The response variable, well, what is the result? What are we looking at? Do the smokers quit? So the response variable is the smoking status at the end. Again, another categorical variable. Did you quit or did you not quit? And what description would best describe this study? Well, it's clearly not an observational study. We already said that. We are giving a treatment, so not an observational study. Is it a comparative experiment? Well, yeah, we're comparing two groups. The group receiving the treatment, the new medication, and the control group, the group receiving the placebo, which is not the treatment under study. So it could be described as a comparative experiment, but is that the best description? Placebo-controlled randomized experiment. Ooh, a lot of words there. Okay. Is it placebo-controlled? Oh, yeah, Group B gets a placebo. So the control group gets a placebo. Yes, it's placebo-controlled. Is it randomized? Yes, our researchers randomly divide subjects into two groups, and it's an experiment. So that answer is better than just calling it a comparative experiment. Is it a confounding experiment? That's a trick question. That doesn't even exist. No such thing as a confounding experiment. Crazy talk. Ignore that. Is it a randomized experiment? Well, yes, but that's not as complete of a description as placebo-controlled randomized experiment. So here we just have the responses we talked about. Now, let's take a look at a study here. What's wrong with this study? Students in a class did poorly overall on the first exam of the class. The instructor wanted to reduce test anxiety, so he had students write an essay about their feelings concerning the next exam. The mean scores on the second exam were higher than the mean scores on the first exam. So the instructor determined that the essay helped reduce anxiety and improve grades. What do you think? What's wrong with this study? Well, there are a lot of things wrong. First of all, first and foremost, we don't have a control group. All the students taking the exams wrote an essay before the second exam. So we can't tell if it was the essay that improved the test scores or if there were some other confounding variables. What else would make students do better on the second exam in a class than the first exam in the class? Well, the second exam could have been easier than the first. Maybe the teacher covered the material better. Maybe the material was just easier. Maybe the instructor felt bad that the test was so hard the first time that they wrote an easier test. Students could have been better prepared for how the instructor writes tests. The first time you take a test from an instructor, you don't know what to expect. That instructor could do things different than you're used to. So second time, you know what to expect. Or maybe you did horrible on that first test and said, oh man, I need to study harder. I can't let that happen again. And that could have been what's going on. You need a control group so that you can see if it's your treatment that has the effect, because all these other things would affect both groups equally. If you have a control group, then you would expect that the second exam being easier, students being better prepared, students studying harder, would be equalized across both groups. The only thing different would be the treatment. All right, so we want to categorize our data as either quantitative or qualitative. So quantitative or numerical data is information that comes from counting or measuring some aspect of your subjects. Quantitative data is numerical, and we can use those numbers to perform meaningful calculations. We can find the mean. We can add up all our values and divide by how many we have, and the answer is reasonable. It means something. It tells us something. Qualitative or categorical data is information about your subjects that allows you to place your subjects into categories. Qualitative data describes some quality of the subjects, like hair color, blonde, redhead, brunette, black hair, dyed hair, like those fun colors of shocking pink or green or blue. Your data tells you what category to put your subjects into. If you have quantitative data, numerical data, you can further categorize it as either discrete or continuous. These words only apply to numerical data. Discrete data is data that can only take on specific numerical values with gaps in between them, such as 1, 2, 3, 4, 100, 157 steps I took today. 0.5, 1.5, 0.5, 1.0, 1.5, 2.0. You can't have any values in between. That is discrete data, and it comes from counting something about your subject. Continuous data can take on any value within some interval, like 0.333333 on and on forever. Pi, which is one of those numbers that goes on forever and never stops. Continuous data comes from measuring something of the subject. Now, we may not be able to measure infinitely many decimal places out. We may only be able to measure up to a certain level of accuracy, but these types of variables can take on values anywhere in between. Your height can be anything from, an adult can be anywhere from so many feet tall, shortest person in the world to tallest person in the world, anything in between. That's continuous data. So, is the following data quantitative or qualitative? And if it's quantitative, is it discrete or continuous? So the number of eggs laid by Katie's eggs, ooh, that's a typo. That should be hens. The number of eggs laid by Katie's hens on a given day. Is that a number or is that a category? Well, it says the number of eggs laid by Katie's hens on a given day. That is quantitative data. So it's quantitative, we can ask, is that discrete or continuous? Are we counting or measuring? You're going to reach under that hen and you're going to count those eggs. That is a discrete variable, discrete data. All right, zip codes of customers at a local store. Is that quantitative or qualitative? Are we measuring or counting? Or are we putting people into categories? Now, this is where a lot of people get confused because they say, hey, it's a zip code. That's a number. Doesn't that make it numerical data? And the answer is no. Those numbers do not count or measure something. They put people into categories. Those categories could be counties or neighborhoods or cities. These are not numbers from counting or measuring. You can't take all the zip codes of the customers, add them up, divide by how many customers you have, and say the average zip code is 816.5.237 and have any meaning to that. This is qualitative or categorical data. Zip codes put people into categories. Now, how about student heights? Oh yeah, that's easy. We're measuring something, so that's quantitative. And that measurement can take on any value within that range. So that is continuous quantitative data. Now, how about viewer ratings of movies, where viewers can rate movies as awful, bad, average, good, or great? That's easy. Those are words. Those are categories. We're not assigning a number. We're not counting. We're not measuring. We are just putting movies into categories. So that is qualitative data. Now, how about gender, where the person putting this into the spreadsheet types in a 1 for male and a 0 for female? This is tricky. Again, people sometimes get confused because they say, hey, that's a number. Isn't that quantitative data? And again, the answer is no, because gender is a category. Even though we're using numbers to code, by looking at people's gender, we are putting those people into categories. We cannot add up all the ones and zeros and divide by how many people and say, ooh, the average gender is 0.75. Doesn't make any sense. That is qualitative or categorical data. And again, here are the answers to those questions that we just talked about. So we have just gotten an introduction to data, categorizing data, looking at variables, talking about experiments and observational studies. As always, if you have any questions, please talk to me. Come see me in office hours, make an appointment, talk on the phone, use WebEx, talk by email, and I will talk to you later.